Alright, hell yeah. We're going to go over all these equations. So this is material mechanics, and this book is gear. And hell yeah, this is going to be one of the hardest parts of the book. These are the transformation equations. And so we're going to go over that. And we're going to try to derive them as fast as possible. I don't do anything fast. But what we're trying not to do is, we don't have to do an overview of what it is. We can do that in other videos. But basically, if we know the normal stresses in the x and y, and the shear stresses, and the fact that if we know one shear stress on one face, they're all equal. So we're up to speed on that. What we can do is we can orient this element at a different angle, and what we're going to get is there's a point where the shear stress goes to 0. That's going to be where these called principal stresses. That's where the x and y's, one of them is going to be maxed. And then at a 45-degree angle to that, you are going to get your shear to be max. And so if your shear is max, then, your principal stresses are probably, I don't know if they have to be at a minimum, or if it's just the average between them, or something like that. But in general, there's an angle where one of these is maxed, and then at a 45-degree angle, your shear is maxed. You know what I mean? Everything else, you can kind of use the equations to see what else, you can kind of find in those. Okay, hell yeah. So we will leave this up just for a little bit, because what we have to do is we have to find, we have to cut this at an angle. And this is similar to having, a bar, let's say it's steel, and you got some loads on it. And sure, if we cut, in this direction, we can do the free body diagram. But what we're going to do is we're going to cut at an angle like this. And so even on our element, you can think of it as coming in and cutting at an angle. And so how they do this, from the textbook perspective, is one is that they're going to rotate this element up from the x-axis. So we're going to have an angle that develops here. And you should try this out. Anytime that you actually take an angle and then rotate it up, just know that it's probably going to be part of a coordinate system. And so if this rolls up theta, then from the vertical, this rolled out theta. And so the derivation actually, and then we have two things going on here. So if our new axes, and when we do rotate this, and don't look at these for a minute, because all we're going to do is just rotate the x and y axes. And I'm going to call this x1, y1. So that's kind of what they do, and they're rotated. And what we want to do is have that element, so here's a quarter of it, and we want to find the stresses on this face, the shear stresses and the normal stresses. And so so the derivation basically says that exactly what I said, but when we this angle forms theta, and then also from the horizontal this angle forms. And so we can make a cut right through here, and this will be our theta. And so now our new axes will be x1, and this will be y1. Okay, hell yeah. So that's kind of the first thing that we're going to do. So we're going to try to not use a whole lot of diagrams. So we're going to just do it from, from the equation perspective. Cool. So I'm going to have some sort of element. It's going to have a sigma x. It's going to have a sigma y. And I don't have to write the other ones. Like, obviously they exist because this element is also a cube of with all sides being same area. This is stress in PSI. It's acting over an area. So this is synonymous with a force vector. A normal force. So these are proportional. But this is a stress diagram. And so, but just as if you had a normal force over here, you'd have to have an equal and opposite normal force. And part of this derivation is that this element is so incrementally small that your stress on this side is going to be the same as that side. But in general, if we have like a beam going on, well, maybe, you know what I mean, maybe the loads are different. If we take a small little slice, maybe the loads are way different from this side to this side. But as we make this a differential slice, well, hell yeah, it's basically the same on both sides. And if we do that in this direction, all three coordinate directions, basically the stress, this is synonymous with a point. So, cool. And if I have sigma y, I also have sigma y in this direction. And I just didn't want to write it, but I guess I explained for 2 minutes. Anyway, cool. And then you have shear stresses. So this is going to be related to positive. The sign convention for the normal stresses, tension is positive, the outward, positive. And we have the y direction and then the x direction. In the shear, we say this is the positive x face because the face is in the x direction. And if the shear stress is in a headed towards the positive y direction, hell yeah, this is positive xy. So it's going to be a positive xy shear. Cool. So even in this problem, hey, this arrow's going in the negative direction. Cool, look at that. It's a negative 4,700. All right, booyah. So now we're going to take a 2D representation, and I guess I don't know why I want to write all these again. But when we have a shear stress on this side, it's a force in the up direction, and we have to balance it. Newton's law is sum of the forces in the y directions have to be 0. These will balance, and so this is unbalanced right here. So on this face, we're going to have a tau xy. Now this is a pressure, but that pressure over the area is the force. So we could say this is also proportional to a shear force in that direction. Cool. And if we have these two stresses that are causing forces, this is causing a moment this way. So we have to have an equal and opposite moment. And so that's where we have this arrow in this direction, and this arrow in this direction. And we would call this tau negative x, negative y. But that tau, negative x, negative y is the same thing as tau xy. So those are equal and opposite. This shear will be tau on the y face in the positive x direction. And this will be tau on the negative y face in the negative x direction. And so these two, because these pressures are causing this rotation across this distance is the same. So these two stresses are the same. So you'll get that relationship that tau yx is equal to tau xy. And you'd usually say tau xy is equal to tau yx, that top one. All right, booyah. So now we have, I guess I don't want to draw this. What we're going to do is we're going to take that angled theta cut. And this is three-dimensional, you know what I mean? So keep that in mind, because we're going to be talking about the pressures or the stresses acting over these areas. And one of these faces we're just going to call A naught. And so if I look to this face on this side, you know what I mean? I'm going to call that A naught. But now we can see that this area is going to be larger. So we have to have a trigonometry relationship showing that. And this area is going to be smaller. So trigonometry is going to be doing that. And so now we go to a free body diagram. And so I'm just going to do a small little one right here. And because, hey, didn't we say this is synonymous with a normal force? Didn't we say this is synonymous with a shear force? And then we have a normal force in the y, normal force in the x. Cool. So, and then we have this shear force down. This shear force is going to be larger than this one because this area got smaller. You know what I mean? So, like these in the cube, this stress over the area, these shear forces would be the same. But if we take a slice, this pressure is now over just a smaller area. So the resulting shear force, this one is smaller, this one is bigger. And then we made a cut, so we have a normal force, a reaction normal, and then we have a shear reaction. And so for our free body diagram, what we want, and the whole general gist is like, hey, we're given sigma y, we're given sigma x, sigma y, and then tau, and I should have drawn it this way, tau xy. So we're given these. These are the things that we're given. And so what we want to know is when we rotate this element, how do they change? And so we're going to, if this is the x1 axis and this is the y1 axis, we're going to call this new sigma, sigma x1, this new sigma, sigma y1, and then this new shear, we're going to call it tau x1, y1. So that's the, you know what I mean, the nomenclature. Alright, booyah. So now we can start in on our cut. So we're going to make that angle right here. And so this is going to be an angle theta. And now these are going to be forces. So let's do the easiest one first. This is going to be sigma x. That's going to be the pressure on this area on A naught. So this is, again, synonymous with a normal force in that direction. But on the free body diagram for this, we're just going to label it with the stresses times the area. Cool. So now this is going to be a shear force down. And this is going to be tau xy A naught. Hell yeah. Okay. So now in this direction, this is going to be my new x1 axis because we rotated it up, you know, from the horizontal angle theta. And this is going to be my y1 axis. And so I'm going to have a theta, sigma x1, and then I'm going to have in this direction, what am I going to have in this direction? Yeah, in this direction I'm just going to have a shear force, or a shear stress, so that's tau xy. And I'm drawing it, yeah, if this is the x1 face, this is tau x1 y1. So yeah, so it's this is a shear stress on the x1, positive x1 face, going in the positive y1 direction. So it's tau x1 y1. And booyah. Now on this, because the area of the cube used to be out here, this area is smaller. And, sorry, these aren't forces. So let's do this one first. If this is the angle, and I know that this length is associated with A naught, then I need to know this length. Now the widths are going to be the same. So like area is going to be base times height, or area is going to be base times thickness, or whatever. But the thickness is going to be the same, but the only thing that's going to be different is these heights. So we want to know what this height is related to this height. So this height just is proportional to A naught, even though this height is whatever this height is times this distance. Or the depth into the page. Alright, so if this is the hypotenuse, let's just do hypotenuse, and I was trying to solve for this, you know what I mean? I would take the hypotenuse, and it would be the cosine of the angle, would give me A naught. Cool, so then we just rearrange for what the hypotenuse is. So the hypotenuse is a naught divided by cosine theta. And I can do this in one step, just being like, hey, I know a side of a right triangle, and I want the hypotenuse. The hypotenuse is going to be the bigger number, and it's going to be associated with this cosine component of the hypotenuse. And so I just know that I'm going to take this length, a naught, and I'm going to divide it by the cosine theta, because this is a smaller number. Taking a number and dividing it by a smaller number gets me that bigger number, the hypotenuse. In the text, they're going to say 1 divided by cosine theta is secant theta. So they're going to say the area of this face, let's call it A prime, is a naught secant theta. So then this force, due to this stress, is going to be sigma x1 a naught secant theta. It's just the way the textbooks write it. I would keep it as just divided by cosine, but whatever. And this stress is on that same area, so it's a naught secant theta. But hell yeah, I am going to maybe not use secants. We'll see, because the same thing as a naught divided by cosine theta, and this is tau x1 y1 a naught divided by cosine theta. So those are equal. Okay, so now we need to find this area. And so we know this component, and we want to know this component. And so these two are the tangent of this triangle. And so I can just write tangent of the angle, and I'm just going to put a little box, is opposite. So that's the thing I want to know, divided by the thing I do know, a naught. So let's just rearrange. Let's get the a naught up there. Hey, so this area right here, let's call it a double prime, is going to be a naught tangent theta. Cool. So the two forces on here, we have a sigma y. So we have sigma y a naught tangent theta, and then we have a shear stress that's tau. And right now you can just say all of these shear stresses are tau xy. You know what I mean? If we have this first face, x in the y direction, that's going to be tau xy. So I'm just going to say, hey, all the shear forces are tau xy. They're not going to make that change in the textbooks until you actually, combine the equations. But we can do that right now. Cool. So this force is tau xy, a naught tangent theta. All right, hell yeah. So let's do that same thing again and just kind of clean it up. So our free body diagram is going to, and we'll make this kind of angle kind of thinner, because that's helpful when we sum the forces in the y and the x. So we have theta. This is going to be our x1 direction. This is going to be our y1 direction. This is sigma x1. But as a force, it's sigma x1 a naught. And yes, I'm gonna go against the textbooks. We're just gonna call it divided by cosine, because you can easily see that's the area divided by a smaller number. Hell yeah, you can see that bigger area. That's an improvement. And then this is not sigma. This is not sigma y1. That would have to be a normal. So this is a tangent. So this is a shear stress on this face that has that area. So we have tau x1 y1 a naught divided by cosine theta. Here, probably should have given myself some more room, but we had sigma x a naught. Cool, that one's easy. And our original one was positive, so this was a positive shear. So these are the positive shear forces. So I'm going to have a positive shear force down of tau xy a naught. On this face, I'm going to have a shear force this way, tau xy. And again, I'm just going to, even though this is this would be the negative y face in the negative x direction, which you would call tau yx. We're just going to say that those are already equal. so these are equal, these shear forces. I just want to draw them in the positive direction, just so when we do our equations, hey, this is representing positive stresses and positive shears. Cool, this area we said was A naught tangent theta. And just, in a moment we need to know that tangent theta is sine theta divided by cosine theta. Because, hey, if we multiply tangent theta by cosine theta, which we will do in a moment, hey, those cosines are going to cancel. Cool beans. All right, and then so we also have a normal stress. That's sigma y, A naught tangent theta. So let's see if we got them all. So we have on each of these faces, we have a normal and a shear, normal and a shear, normal and a shear. And they're all the shear stresses multiplied by the areas. And so these are all forces. So now what we're going to do is we're going to sum the forces. Now, do not sum the forces in the y and x direction, because what we're trying to solve for is this term, and we're trying to solve for this term. So if we sum the forces in this x1 direction, let's do that right now. Sum of the forces in the x1 direction is 0. Hey, I just have this. It's 100%, so we just have that term. So we have sigma x1 A naught divided by cosine theta. All right, that's going to be in the positive direction. And then this is perpendicular, so this is nada. And everything else in these problems, the whole idea is that you're given everything else. We know these sigma x, sigma y, and shear. On the rotated element, I'm going to have an equation that's based on sigma y, sigma x, shear. And I'm going to try to solve for the new normal x, sigma x1, given those inputs and this angle. So that's kind of the equation that we're shooting for. All right, hell yeah. And so I guess I've gone over this, you know what I mean? So when we sum the forces in the x direction, this is going to be nada. But all four of these components are going to have some sort of component. So in the textbook, they're going to start with this sigma x first. And so it's perpendicular this way. And so we have two things, I'm going to pull out this method again, where if this was my original axis and then I rotated it up, hey, this angle just got rotated theta. And then what happened is that this vertical, also you could say it got rotated right here, or you could say that from the vertical we have this angle formed. And I'm going to call this the bow tie method, because if I have the horizontal and I rotate this angle up, I can take this line, past, through the horizontal, and I can get these two angles, from the horizontal. This is how I'm going to easily see the components, the horizontal component. So if I see a horizontal component, I'm going to be like, hell yeah, from this arrow, I know that we have kind of like, we have this bow tie method. I'm just going to call it the bow tie method, because hell yeah, you got a little bow tie. And now I know that this is theta. Put some sun shining rays on it. The vertical component would be this direction. The horizontal component is in the x1. So cool. So this is going to it's going to be negative. It's going to be in the negative x1 direction, and it's going to be the cosine component of this. So we're going to have sigma x A naught cosine theta. Booyah. Now we're going to go to this one. Same thing using the bow tie method. If I have a vertical, and we rotated everything, use a corner of a sheet of paper, then hell yeah. This rotation is going to cause those two angles to form. And so if I come to this force, I'm just going to come to the tail. I'm just going to draw in that angle and be like, hell yeah, I got an angle there and an angle there. So cool. So I can see my theta, and now I actually want the sine component. Sun is shining on the sining. I don't want the adjacent component. So this will be, and it's going to be this is going to be in the negative direction too. So negative tau xy A naught, and it's the sine theta. Hell yeah, so we did our first two. Moving on to this face, and then we're done, right? So we're going to do the we're going to do first the normal stress. That's how they do it in the textbooks. But it's a vertical, you know what I mean? So again, hey, what's our angle? We're going to be coming in here, a little bow tie method. And so this is theta, this is theta. I don't want the cosine component. I'm sorry. And you always got to say, hey, this vector is your hypotenuse. So if this is the angle, you know what I mean? Make sure you treat this as your hypotenuse and then drop it down. You know what I mean? Because if I'm saying the component in this direction and this direction, so now I can see that this is the x1, this is the y1, you know. And so this is going to be negative x1, and we want the sine component. Sun is shining on the sine. So hell yeah. So for this force, we're going to also have a negative sigma y a naught tangent theta times sine theta. Cool. And then this one, the shear, you know what I mean? You can even just see it's kind of going in the negative x direction. But it's horizontal. And so we rotated our element up like this. So let's come here and do that little bow tie method. This would be theta. And then mirrored image, this would be theta. And so I don't want, and this would be the hypotenuse, so drop it down and make a right triangle. And I don't want the vertical component. I don't want the sine component. I want the cosine component. So this, I'm going to take negative tau xy a naught tangent theta and cosine of the angle. All right, booyah. And we made our paper probably pretty messy, but those are the sum of the forces, and those are going to be equal to 0. Now we're going to sum the forces in the y direction equal 0, and hell yeah. Oh, and then the whole idea was this, is like we know all these terms. Like I said, sigma x, sigma y, and shear, we know them. What we would do is just solve for that. And so we would get those 4 terms to the other side, know that we can just cancel out an a naught, and then multiply by cosine. It's that simple, you know what I mean? And then you literally have your stress. So if one of the problems says, hey, let's rotate at a 25-degree angle, can you find sigma x1? Well, you can just do this process, take these to the other side, drop out the a naught, and then just multiply that by cosine, and use that as your equation. You know what I mean? It's not the luxury transformation equation that we'll hone in on, but hey, it's that equation works, and you could even use this equation. Alright, hell yeah, my camera died, and that's just a good sign to just kind of move on to the next phase. So we're going to sum the forces in the y direction, and we can kind of go a little faster, even though a little messy, but we have tau x1, y1, a naught divided by cosine theta, and then that's going to be in the positive y. We're going to come over here, and hell yeah, this force is like this, and then this angle in the y is, making an acute angle. So this will be a positive value. So this sigma x a naught, we want to know its component in this direction. And hell yeah, we even have our bow ties already done. So this is going to be the sine component. So we're going to be plus sigma x a naught sine theta. Now for this one, so we have, here's our angle, and we're going to have the cosine. So this is going to be negative. So we're going to be negative tau xy a naught cosine theta. Alright, moving to this one. Yeah, we already have our angle, so this is becoming a lot easier. We're going to be negative y1, and we're going to do the cosine. So for this one, we're going to have negative sigma y a naught tangent theta cosine of the angle, and then for the shear, that's going to be this one. Here's our bow tie, and I want the vertical, and this is going to be in the positive direction because this is the x1 direction horizontal, and then hey, we're in the positive y1. So we got positive tau xy a naught tangent theta, and I said we wanted the sine component. So we have sine theta. Alright, booyah. So now we can sum the we can solve for sigma x1, and we're going to solve for sigma tau x1 y1. And so these are you'll usually see this one and this one in order, but I mean, I just kind of put the y1, but the first two you're going to solve for are the sigma x1 and tau x1 y1. Those are the first that are going to come out of this free body diagram. Now they're not going to look like this, and so what happens is that this is an equation where you just have cosine, where you can take a differential equation of this quite easily. You know what I mean? If I just have a cosine and I have a sine, you know what I mean? Derivative of cosine is negative sine. Derivative of sine, hell yeah, it's going to be cosine. And we can talk about that. But when we solve for sigma x1, we're gonna get cosine squareds. You know what I mean? Because and let's just, I don't want to write a lot, but let's just pretend like these are on the other side. So get them to the other side. And this, if you don't want to write a lot, let's just do that. So we have these are equal to 0. That's the same thing as just like scribbling that out. Putting the equal sign here. All these become positive. And then we're going to drop out the a naught everywhere. And then I can just multiply by cosine everywhere. So this becomes cosine squared. This becomes sine theta cosine theta. And again, tangent is sine cosine. So when I multiply by cosine, the cosine cancels, and I get sine squared. And then this is same thing. Sine cosine multiplied by cosine. The cosine will cancel, and I'll have sine theta cosine theta. So that is equal to sigma x1. And I guess I can write it, maybe we'll write it on another sheet of paper, because then we have to make this look like that using trig identities, and we're going to go, you know, kind of slow roll that process. Alright, so this is equal to 0. Sorry I didn't put sum of the forces are equal to 0. This we're going to have, you know, if I play that same game and put an equal sign here, this for sure becomes negative, positive, positive, and this becomes negative. And then I'm going to have drop out the a naughts, and I'm going to multiply this by cosine theta. So I'm going to multiply the other side by cosine theta. And here we have sine. This is sine divided by cosine. Those cosines would cancel. And I'm going to have sine times cosine. And so, or I could just say, bring over the cosine, and that'll cancel this cosine under the tangent. Keep this one. And I'm just going to have sine theta cosine theta. Sine divided by cosine, and then when I bring over a cosine, that cosine will cancel. I'm going to have sine squared theta. Cool. So now I can, let me write these on another sheet of paper, and then we'll go from there. Alright, hell yeah. So we rewrote our two equations, and we have sigma x1 and tau x1 y1. So this is if we want to throw in an angle, and now we have sigma x1 and we have tau x1 y1. Now in the textbooks they're going to be like, hey, you can easily find sigma y1 just by throwing the angle plus 90. You know what I mean? Because if I say this is the angle theta on this face, then if I went theta plus 90, I would have the perpendicular face here. And so that's how they do that. When you do throw in a theta plus 90, you're going to get a, how does that work? Yeah, I think, well, oh yeah, that's fascinating. If you threw in a theta plus 90 right now, what you're going to get, this would be sine theta, and it probably would be a negative sine theta. And so, don't quote me on that, but you would have to look at your quadrants and see if it's a factor of 90, it's going to change from cosine to sine. But in a moment here, we don't want this like this, because the other most important thing that we're going to try to find is the maximum the maximum stresses. So the maximum normal stresses at some sort of angle, and then the maximum shear at some sort of angle. And so that's going to be designated as, this is still in the, well, no, this is going to be sigma 1 and sigma 2. And depending, sigma 1 could be in the x direction, or it could be in the y direction. You know, sigma 1 could be, the max could be this one. Sigma, and then, and whatever, and when we find the max stress for one of them with an angle, the other one is going to be just associated with that. And those are going to be the principal stresses, and what happens is that your shear stresses are 0 when we find that angle. So whatever angle makes the shear stress 0, that is going to be the principal axes. Alright, cool. And it's just like, well, if that's the case, like, couldn't you actually just solve this for 0? But anyway, we'll see what they do. What they do is that they say, hey, if there is a maximum from this, if theta varies, and you do get a maximum of this number, the derivative of this, you set that equal to 0, and then you solve for the angle. And so we need to get this equation without these multiples of sines and cosines, without sine squareds and cosine squareds. And we can't just say, hey, this is 1, because you can only say sine squared plus cosine squared is 1 is if your terms, your factoring terms are the same. And so what we use is the double angle theorem. And so it's good to do this. You know what I mean? And you should, so here's like the light bulb moment. You'd be like, hey, I don't like this term. Can I get it into something simpler? And we will be able to. We're probably going to get it, some of the half angles are like, you know what I mean? Half, 1/2 plus 1/2 cosine 2 theta, or something like that. And there could be a negative here, and this could be a sine 2 theta. So just in general, that's the form that we're looking for, and we're happy about that, because I can differentiate half, that would go away, and I can differentiate something that's just 2 theta. It's just the u substitution, or you can just, when you differentiate it, you just be like, pop out the 2, however you want to do that. But that's kind of the next step. And so I always kind of just draw the 2 angles, and we're going to call this theta and theta, because you could call it theta divided by 2, I don't know, but anyway, so just for this we're going to call it theta. No, you need to call it, because this angle is theta, and this angle is theta, and it comes out of this double angle theorem. And so the double angle theorem, you can do 2 things with it, especially if these are the same. Hey, maybe, and what we have to visualize is that this distance, the hypotenuse, is 1. And so if the hypotenuse is a value of 1, what you would want to do with double angles is be like, hey, I want to know the length of this line. Well, that's going to be sine of this bigger angle. And that bigger angle is 2 theta. So the length of this line is going to be sine 2 theta. Multiplied by 1, you know what I mean? The hypotenuse times sine 2 theta is the height of this line. So we're just going to neglect the 1's, but just keep in mind that that is that distance. You could do the double angle theorem and throw in a value here of like 5 and just carry it all the way through. If that could be more helpful, to be like, oh, I see that this is a distance of 5, and this is probably a little bit less, and so it's going to be 5 sine 2 theta. Alright, so that distance is going to be sine 2 theta. And so now what we're going to try to do, well, yeah, and then if I was trying to solve for this distance, this would be cosine 2 theta. So that distance is cosine 2 theta. And let's do the cosine one first. and see what pops out. We'll probably have to do both. I think you need to do both for this one. And so I mean, you don't have to get too techy. There's only two things you can do. You start with this hypotenuse, and you could and treat it like a hypotenuse, and then you're going to reflect it onto this one. So you're going to make a 90-degree angle, booyah. And so now you could either find this, you could say that this is cosine of theta, and this is sine of theta. And then if we bring this one down again, so this new hypotenuse is cosine theta. And then, and if I bring it down again, this distance to here is going to be cosine theta, cosine theta. Because if this is the hypotenuse, I'm going to take the hypotenuse and take the cosine of the angle. So that's what happens with this, with the double. So just always think of like, hey, this is a hypotenuse of 1. And then if I find the cosine component, I can treat this now as a hypotenuse. Booyah. Alright, so, and then to finish the cosine one, we're going to say, hey, this is the sine component. Because I overshot it. You know what I mean? I want to know that this is I want to get an equation that says cosine 2 theta is equal to these other terms that I have. And so I'm going to say it's equal to cosine squared theta. But now we have to subtract this term. And this one's going to be the sine of this angle. And then just know that if we have to use this kind of trick that, so all I've done so far is just done this, taken this hypotenuse and then found this sine component. And so what I'm interested now is taking this sine component and, well, let's draw this angle in. And I want to know the sine component right here. So this sine component right here would make up that difference. So I take the sine of this and then the sine of this. So this is sine theta, and then I'm going to treat this as your new hypotenuse, and then I'm going to take the sine of that. So sine theta of that hypotenuse. So this term becomes sine squared theta. Alright, hell yeah. And if you have a hard time seeing that how these angles form, well, it's just like, hey, if I took this down to the vertical, then I would have, see how I'm rotating this? So this is my 90 right here. And if I rotated this down, I rotated it at distance theta. And then so now here's my vertical. And when I rotate this theta, this opens up a distance theta. So that can be useful for that. Because for that one you need that vertical line. Alright, let's draw this one more time. And that was to find, okay, and then we got to finish this. So cosine 2 theta is going to be cosine squared theta minus sine squared theta. And this is going to be used right here because I have a cosine squared theta minus a sine squared. So if I take these two terms and factor out the tau xy, I'm going to have cosine squared theta minus sine squared theta. So this is the first identity that you're just like, oh, hell yeah. So this just becomes cosine 2 theta, and we're done with that identity. Alright, booyah. So, now, from this, I mean, don't stop now, or don't stop here, because, like, you use this to get this, you know, you use this form to just take any sine or cosine and get it to like this. And to do that, you just choose one. If I was trying to find sine squared theta, you know what I mean? Let's say I had this sine squared theta up here. And so I'm going to say, what do I know? Pythagorean's theorem says that this is sine theta, this is cosine theta. This would be like A, B, and C. And Pythagorean's theorem says that a squared plus b squared is equal to c squared. If I'm trying to find the hypotenuse, hell yeah, we already know that sine squared theta plus cosine squared theta is 1. But I think it's trickier to be like, hey, if I have cosine squared theta, which is just one of the sides, how do I get that? Because I would treat this as, hey, I would say this is, if this is the hypotenuse, I would say this is the square root of both sides squared and added together. But if I'm just trying to find this value of cosine, I would say this is the square root of the hypotenuse squared minus the side squared. You know what I mean? So this is just always a useful equation. So that means that that's cosine theta. Cool. And then, like, I know this more than, you know, if I'm just trying to solve for cosine squared theta, we'll just square both sides. And so, same thing. Cosine squared theta is going to be that bigger hypotenuse minus sine squared theta. So that's kind of how I think this is a little bit more difficult to kind of see just on the fly, to be like cosine theta is 1 minus sine squared theta. Now, if you're just memorizing this equation, well, hell yeah, cosine theta is 1 minus sine squared theta. But I like to visualize things from a Pythagorean's theorem to be like, hey, this is going to be that hypotenuse squared minus the other side squared. You know what I mean? And if I took the square root of that, that would give me that length. So I like to think of what I'm doing here in terms of this equation and not just this identity and moving a value. I think the second you get into an equation that loses its meaning and you're just like rearranging it, I think there's something to be gained from what I just said. Cool. So this value becomes 1 minus sine squared theta. And cool, we're actually going to subtract it by another sine squared theta. So this becomes 1 minus 2 sine squared theta. And now you can kind of see that, hey, if I can solve for this, and I'll have this in terms of something differentiable and like a 1/2. So what should we do first? Should we get this to the other side? So 2 sine squared theta, and then let's get this to the other side, is equal to 1 minus cosine 2 theta. And so all we did is get these two switched, and then let's divide by 2. So this sine squared theta I can replace with so I'm going to 1/2 minus 1/2 cosine 2 theta. I would write it like this, you know what I mean, compared to just 1/2 1 minus cosine 2 theta. You know what I mean? Because if you write it like this, it'll be a little bit easier kind of to see what happens. So let's do that right now. So we have 1/2 minus 1/2 cosine 2 theta for that term. So we're going to have sigma y times that, sigma y times negative 1/2 cosine 2 theta. Now we can do the same thing for, like, even right here, it's just like, well, couldn't we do that same thing and solve for cosine 2 theta? So hell yeah. And then we're going to be, so we can solve for this with this same identity. So this identity helped us solve for this one, you know, sine and cosine. And that makes sense because the cosine identity is where you get 2 cosines to show up, and a cosine squared, and 2 sines to show up, a sine squared. So when I come through here, it's like, okay, this identity works, this identity works, this identity works, this identity works. In this identity, we don't have a sine theta, cosine theta. So that's where we'll have to come over here and say, hey, let's find, if this is 1, let's find this distance. This is going to be sine 2 theta. And we're going to have that equal to, and so we're going to do that in a moment. Alright, so let's solve for this cosine. Same thing. Let's just say this is sine. What do we know what we just talked about? 1 minus cosine squared theta is this. I'm going to have a minus, so I'm going to have minus 1 plus cosine squared theta. I'm going to add it to another cosine. squared theta. So I'm going to have negative 1 plus 2 cosine squared theta for this term. And then I'm going to solve for this. So let's get the 1 to the other side. So I'm going to have 1 plus cosine 2 theta is equal to this. So now I'm just going to divide by 2. So I'm going to have 1/2 is equal to cosine squared theta. Now I can sub this into here. So let's do that. So we're going to have 1/2 plus 1/2 cosine 2 theta. Hell yeah. And so now let's do this one. And I get you can just play around with it and see, but I mean after you've done it a while, yeah, you're just like, okay, if I'm trying to find this cosine, that might be the easiest one. It's just like, well, take the cosine of this one and take the cosine of this one. You're like, oop, I overshot it. So let's take the sine of this one and the sine of that one. So that's kind of how, I mean, there's a little bit of memorization there. Now for this one, I'm trying to find the sine component. So yeah, maybe the first thing I do is just, you know, take the sine of this one, and then maybe it's like, ooh, I know this is theta, and let's take the cosine of it. That's going to be this component. Booyah. And so then let's take the cosine of this angle, and then, ooh, it really spells it out. I'm just going to take the sine of this, you know what I mean? And then that gives us. So this one, probably a little bit, I think it's trickier because you got to use a sine and a cosine. But let's spell that out. So if this is 1, I'm going to, and what would be the easiest, probably the easiest thing to do is like, hey, take the cosine first. So this value is going to be cosine theta. That's our new hypotenuse. And now we're going to take the sine of that. Sun is shining on the sine end. That's going to be that height. So I'm going to take this hypotenuse times sine theta. So this value right here is cosine theta sine theta. All right, done with that one. And then we need to find this height. I'm going to take the sine component. That's going to be this. You know, here's my 90 degree. I'm treating this as my hypotenuse. I got to drop this down to a 90 degree. And then I can see that, hey, this is my new hypotenuse. This is the angle theta. I'm going to drop this down to a 90. And booyah, it's just perfect. So, and so this value right here was sine theta. That's my hypotenuse. And I'm going to take the cosine of that to get that length. And so cool. So this is sine theta cosine theta. Now, you can just, it doesn't matter the order these go into. And so what we have here is the fact that I was trying to find the sine of 2 theta. That's this vertical component of both of these angles combined. That's going to equal both these added together. That's going to be 2 sine theta cosine theta. All right, hell yeah. And so what we see is that this term pops up a lot. And so just get the 2 to the other side. And now everywhere I see this, I can just put a 1/2 sine 2 theta. So let's do that. Let's even write it out 4 times. 1/2 sine 2 theta. Whoops, sorry about that. 1/2 sine 2 theta and 1/2 sine 2 theta. All right, sweet. So now we have to start simplifying this. So let's see, 1, 2, 3, 4 terms. So these are the same, and these are the same, and we're adding them. So we're adding a half of something to a half of something. Half an orange, we got a full orange. So let's just write that one. Well, let's keep that in mind because typically how we write these are sigma x first. And so, so this is going to be sigma x divided by 2 plus sigma x divided by 2 cosine 2 theta. This is going to be sigma y divided by 2 minus sigma y divided by 2 cosine 2 theta. Cool. So let's just focus on this term. We already know this, these two terms are pretty simple. So in the book, what they're going to say is, hey, let's combine these. So this is going to be sigma x plus sigma y divided by 2. And then we can do the same thing for these. We have this. We can factor this out if we put these two together. You know what I mean? So I guess instead of factoring something out in front, they're going to factor it out behind. So they're going to do sigma x minus sigma y divided by 2 times cosine 2 theta. So we factored this out, but typically you would put something in parentheses. We're just putting that something in parentheses right there. And I can put this in parentheses. Hell yeah. Okay, so now for this, we said we were just going to have a full one. So we're going to have plus tau xy, and we're just going to have sine 2 theta. Alright, booyah. Did we do good? You know what I mean? Let's see if we even got it. Sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 cosine 2 theta plus tau xy sine 2 theta. So that'll be the first pen drop. I mean, even just to get there, you know what I mean? Holy hell, that's a lot. That's a lot of, and especially if you actually go through. I don't think there's any reason to do the trigonomic identities. And this is my new MO. Anytime, like if you just don't know how to do a proof, that's fine. Use the equation. Like there's plenty of times if you never knew how the derivation of the area of a circle, hell no, just use the equation. Like just get on with life and use the equation. But if part of the learning of a new topic is a derivation, like my MO is like anytime I get a simple basic problem, you know, and these are, at the end of the day, these are just going to be take 3 numbers and plug them into a dumb equation. But then you just lose all sense of reality. And so with even just and this was good because even I'm learning of like why we would want to use trig identities is because we need to find the if we didn't have to find the max value, oh hell no, just leave it like this and just get on with the day. But we're going to have to take the derivative. We're going to have to take the derivative of this. So if we say, hey, as my angle incrementally changes, I'm going to focus on the change in sigma x1. And when sigma x1 doesn't change at all, you know what I mean? It's changing, ooh, it's not changing. That's either going to be a max or it's changing, ooh, it's not changing. I moved a theta. I moved theta from here to here, and sigma x didn't change. You know what I mean? So that's the definition of a derivative. And so if I take the derivative of this equation and solve for where that change does not occur or equal to 0, then I can solve for that angle theta. Alright, so we have sigma x1 is equal to that, and we have our first. So now that we've fully, you know what I mean, got our first transformation equation, I'm just going to probably pull it off this sheet. So sweet. So now let's get tau x1, y1. Okay, so here we had to get this cosine squared theta and then minus sine squared theta. And like you could do this 2 different ways. So let's do it the slow way, because didn't we say, I mean, like the fast way is just when you get to here, when you say that cosine 2 theta is cosine squared theta minus sine squared theta, hey, this is a treat. Like this is, for this problem, that's pretty cool, because that's like a little treat that you get this right here, just all in one go. If you solved for what cosine 2 theta is, which we did that, we said that, where is it? So cosine 2 theta is this. So let's write that out. And let's factor this. So again, let's have tau xy is in both of these terms, and then we're going to have cosine squared theta minus sine squared theta. we said that cosine squared theta is this. So let's write that in. 1/2 plus 1/2 cosine 2 theta. All right. And then we said that sine squared theta was this. Cool. 1/2 minus 1/2 cosine theta. But we need a negative sine squared. So this is going to be just the signs are going to change. So we got negative 1/2 plus 1/2 cosine 2 theta. All right, so we have a half minus a half. Those go away. And we have a half plus a half. Sweet. So we just get cosine 2 theta. And so that's the slow way to get there. And so because a trigonomic identity is going to give you these. They're going to give you these two values. They're going to say sine squared is equal to that, and cosine squared is equal to this. They're not going to be like, hey, cosine squared. They might. Cosine squared theta minus sine squared theta is that. But hell yeah. All right, so yeah, let's simplify this. All right, booyah. So like the book does, they deal with the sigma x and sigma y's first. So it looks like we're going to have a, yeah, on both of these you're going to have a 1/2 sine 2 theta. So I'm just going to do this. I'm going to factor that out. So we're going to have a negative sigma x plus sigma y. But now here's the bizarre thing. You know what I mean? Like they just choose to what do they do? Oh yeah, they choose to what? Can you even do that? Multiply by a negative 1? Oh, bizarre. Yeah, we'll see in a moment, so I don't mess up. But yeah, we do have this, and then we're going to multiply it by 1/2. So we have 1/2 sine 2 theta. I swear, negatives like ruin me. But yeah, so what they do is just they like, can you factor? Yes. Well, can you factor through a negative? Oh, that's confusing the hell out of me. But I guess I'll just spell it out. What they do is negative sigma x minus sigma y. And I guess if we had to factor this out, we would have negative 1 sigma x, and then we would have negative 1 sigma y. So we would have negative sigma x plus sigma y. Yeah, that's the bummer. I don't, like, why do I not see that? Oh, so I guess it's you can factor out the negative. Is that how you would do that? I don't want to waste too much time. But if I had a negative 1 here, and then I said this was, yeah, check this out. I'm going to multiply top and bottom by a negative 1. Holy hell. So that is genius. And then we have sigma y. So now I can factor out a negative 1. And so if I have a negative 1 outside the brackets, this becomes, sorry, and this is sigma x. So this becomes just sigma x, or positive 1 sigma x. And yeah, sigma x, and this, and if I factor out, I factor out the negative. So I'm taking these two out. I still have 1 divided by a negative 1, sigma y. And so that gives me negative sigma x minus sigma y. So that's, yep. I'll have to make a separate video, but yeah, that's bizarre. You know what I mean? It's just really difficult for me to see that. The fact that, hey, I just multiply a negative out, just get the negative out here, but it's like, how do you factor out the negative? I think that makes sense. Pretend like this has 2 negatives. So again, we're going to have negative 1 sigma x plus negative 1, and I can even, you know, I can put as many 1s here as I want. You know what I mean? Just so it doesn't look bizarre. Sigma y. And then if I factor out a -1, I'm going to have -1 factored out. So now I'm going to have sigma x. One of these -1s gets factored out. So I'm going to have 1 divided by -1, 1 sigma y. I just didn't want my, the numbers to just disappear. So -1 times -1 is -1. And if I have a -1 in the denominator, it doesn't matter if it's in the denominator or numerator. It's still -1. All right, sweet. So that was a pretty good little segue. So that's what they do. They take this, and let's just do one step further. We're going to divide by 2 and multiply by sine 2 theta. So those are the steps on that. That is going to be these sigma x, sigma y terms. Now we have these two terms, which we said combined, just plus tau xy cosine 2 theta. Hell yeah. And we're done. So this is tau x1, y1. That right there is tau x1, y1. We come to our sheet of paper, and we see that tau x1, y1 is negative sigma x minus sigma y divided by 2 sine 2 theta plus tau xy cosine 2 theta. Booyah. Alright, hell yeah. So we got our first two equations, and we're going to get sigma y1. Now I think, I'm going to do it in a separate video. But what we started out with was an element, and then we had this as our angle, and that was associated with this x1 being at this theta. So, and this is also that I'm kind of picking up on is, hell yeah, if you have an angle and it's perpendicular, so this is a positive slope, its perpendicular is a negative slope, and it's what is it? Yeah, it's the inverse of it. It's 1 divided by the angle, but whatever. So what we could do is take a slice, and if we're gonna cut, we could just cut it right here. And so here's our angle theta. And so if we take that cut, guess what? This is sigma y1. And this is the x1 direction. This is the y1 direction. So this would be tau on the y1 face in the x1 direction. You would solve for this, and it wouldn't matter. It would be the same thing as solving for tau x1, y1. We just said that those are equal, right? But hell yeah. So then you could say this area is a naught tan theta. This area is a naught secant theta, or a naught divided by cosine theta. This area is a naught. And then you have two forces, and let's go back to our element. If we're saying this is positive shear, this is the positive face. So positive shear is this way. It's always good to write positive shear. And I'll go over this, Again, they'll say like, hey, sure, this is positive face, positive direction in the y, that's positive shear. And then they just say like, hey, these arrows touch. Don't do that, for your first 10 rodeos. Like, say that this is causing a force up, it's got to be balanced by a force down. That's going to cause a rotation this way, so I need a rotation equally that way. Hey, this force could stop that rotation, and if I introduce this force, it has to be equal and opposite. And basically, once you get down to the moments, this moment has to equal that moment. The forces are the same because the areas of that cube are all the same. But it's good to draw in a positive shear, so when I get to here, I can be like, ooh, this is positive. And this is positive in the normal direction. This is positive sigma y, and then this is positive, because positive face, positive x. And hopefully I got that right, because I swear, like, there might be a hiccup here of this sign, of even just rotating it like the. No, I think we're good, because hey, this is positive up, this is positive that way. So if I rotated it, this would still jive. If I rotated just a slight little angle, So sweet. So yeah, you can, and then you could solve for, sigma y1. I mean, you could solve this again if you wanted to. You don't need to. You know, again, you can solve for this tau y1. So if I do have a rotated angle, what we solved for was the tau x1 y1 right here on this face. If I did this, I could solve for tau y1 x1. You know, I could do those same equations, but guess what? They're going to be equal. So that could be a little homework thing, just to be like, ooh, I want to prove that they're equal. You know what I mean? Cool. The other way to make this a good homework assignment also is to like take a cut on this square, and you know what I mean, I cut out this but leave this chunk. Holy hell, because now you have an a naught, you have a naught tangent theta. That means that this area is a naught minus a naught tangent theta. This area is still a naught divided by cosine theta, and this area is a naught. But yeah, this term seems like that sucks, and I'm going to have a normal, a shear, and then I'm going to have a normal and a shear, a normal and a shear. You know what I mean? So you're just going to get more terms if you use that, but you'll get the same answer. So that's kind of fascinating. That is useful to work on your skills of grinding through algebra and trigonometry. And just to also prove to yourself that, hey, like the trigonometry works. It doesn't matter what the angle is. We solve for, you know what I mean, this angle, it doesn't matter if this angle is 0 to 360. The slice, what will happen is we'll just rotate our x1 and y1 axes. So we'll have x1, y1. And so if we rotate it, you know what I mean? So if I don't rotate it at all, x1 is just, you know, the same. Sigma x1 is same as sigma x. Sigma y1 is same as sigma y. If I rotate it 90, guess what? Sigma x1 is equal to sigma y, and sigma y1 is equal to sigma x. You know what I mean? And so, and then we're back to normal, and then rotate it. You know what I mean? So there you go, 270. That thing happens again. All right, so where do we? I think we need to find the max. So we found. Oh no! I did this because that's why. Because we would need the equation for sigma y1. And so let me get my equations. Whoop. All right. So what we do is we take this equation for sigma x, and we just throw in an angle, because if we threw, let's say we have an element, we want to rotate it up 5 degrees. Like, that's all we're interested in is 5 degree rotation. I can solve for sigma x1. That is going to be, and so what I just said is if I rotate something 5 degrees, so let's do it, sigma x, sigma y. So if I rotate it 5 degrees, cool, I'm going to find sigma x in this direction. Let's say I rotate it 95 degrees. Okay, I'm going to be, so see how sigma y was right here? I'm going to rotate x, this axis, 5 plus 90, and I'm going to be up here. And guess what? I'm going to find the normal force in this direction, which would have been the normal force, sigma y1, at angle of 5 degrees. So when I take sigma x1 at an angle of 95 degrees, I get sigma y1. And so I'm going to go over this because this is, I think this is good. I'm going to use this method to figure out what the equation is going to do. What are the sine components going to do? And because we're going to have to double, you know, we're going to have to take that 5 degrees and multiply by 2. So the cosine is going to be cosine of 10. So let's just do that. And cosine of 10 is this length right there. When I throw in a value of 95, 95 times 2 is 180 plus 10. It's 190. So I'm going to be over here. And then I'm going to have cosine of 190. And what's going to happen is this was a positive cosine, and this is going to be a negative value. And so, so if I'm using this equation, so here's the deal. If I just want to throw in 5 degrees into this equation, I'm going to get this value. But I want to throw in 5 degrees and output sigma y1, which I could just use this equation and keep inputting 95, but I just want an equation where sigma y1 is a function of this original angle 5 degrees. So if I threw in 5 degrees into this, I would get this positive cosine. What I want is this negative cosine. So this just becomes negative cosine 2 theta. So cool, we're done with that one. Now we have another one to do. We're going to have sine of 2 theta. If I choose an angle of 5 degrees, multiply it by 2, that's going to be 10 degrees. The sine of that's going to be that height. So again, if I throw in 5 degrees into this equation, I'm going to pop out this positive height right here. What I want to do is throw in a value of 95 degrees, because if I did that, I would get sigma y1. When I throw in 95 here, I got to multiply that by 2, and that's going to be 190 degrees. So I'm going to be all the way down here. And sine of 190 degrees is going to be a negative value. And so that's what I want. If I throw, I want this angle to be 95, and I want to get this negative number, because that's going to give me that sigma y. But what I want to do is have a sigma y equation where I just throw in 5 degrees. So if I throw in 5 degrees here, I'm going to get this positive value. I want it to be this negative value. And so I just throw a negative sign right here. So I have negative sine 2 theta. So I don't know. There's probably easier ways to go through that, but that was the way that I explained it to myself. So when we throw in sigma y, the only thing that's changed is this sign becomes a negative sine 2 theta. That negative is displayed right there. This becomes a negative cosine 2 theta, and that negative sign is displayed right there. Sweet. All right, so we did it. And that saved us all that effort of going through another free body diagram in the sigma y direction and going through trigonometric identities again. Booyah. So we have our 3 main equations, and this gets us all the way if you have a graphing calculator. Because if I throw in these equations into my graphing calculator, you know what I mean? This is 0 to 90. Yeah, that's 0 to 90. And I have, yeah. And I don't know which is which here. But I think the blue and black are the normal stresses. One's the x, one's the y. And when the normal stresses are averaged, when the normal stresses are equal to each other, because I think that came up in this problem. It's just like, hey, look at this. The normal stresses are equal to each other. The shear stress is max. And I think this is just this problem, so don't quote me on that, you know what I mean? Like, I don't want to make too many assumptions based on these equations, but these equations, you can look to see what properties they have. And the other thing that happens is when the normal forces, when the shear is 0, hey, we get a maximum. One of these normal forces is maxed. And so this probably is this problem, where when the shear is 0, hey, one of these is maxed. The other one's a negative value. But the difference between these two is also at a maximum. Like this might not be... and does that mean that this is a minimum? as well. Like there's no other location that it gets lower than that value. Yeah, so principal stresses is a max and a min. I don't know. But it at least is a maximum. Yeah, I'll have to look that one up. Is that what that means? One's a max, and if one's a max, the other's a min? Or can you have two localized maxes, one's just not as high? I'll have to look that up. But anyway, I mean, I guess not to lose everything, the whole point is to find the maximum normal stress, because that maximum number would be important. You know, if I have a setup where I know these three numbers and they look kind of average, what happens is you're just like, no, we actually on this maximum angle, we get a value of 13. And this, look at this shear stress more than double. So if we design something to take this shear stress and maybe had a factor of 2, we're going to exceed it. So that's kind of why we do these diagrams and why we go through this method. And so now, yeah, if you can just throw these into your calculator and find the maxes and mins. And you didn't even need the trigonometric identities to do that. You could have just used the equilibrium equations, got to, you know what I mean, the safest place that we got to, like right here, sine theta, cosine theta, who cares? Throw it into your calculator and just graph and find those maxes, find those mins. And I think that is another useful strategy where you don't lose just all touch of reality. These equations, because they're so like massaged, they can, you know, they're almost meaningless in that regard, like from the equilibrium equations. All right, hell yeah. So we're going to derive, the first one we're going to derive is sigma x1. So we're going to take the derivative of sigma x1 with respect to theta. Now, we're going to have to use a u substitution, because if we, and I mean, you could even say this is a product rule. You know what I mean? So if I have a constant a and then a cosine of u, you know, the derivative of this is the derivative, the first times the derivative of the second. So we would have a times the derivative of cosine u du plus the second cosine u times the derivative of a du. This is a constant, so this would go away. You know what I mean? So it's good to not just use so many shortcuts when it comes to derivations, and you know what I mean. But we're gonna do this one. So this u is going to be 2 theta. And we're going to say the derivative of u with respect to theta, because we have a theta here, this is going to reduce in power. The power is going to come down, and we're just going to get 2. And then so for our differential equation, you would set this up as this. So we would have, I'm just going to call these constants. So we have a plus b, and then we have cosine, and if I say this is u, how do we do this? Yeah, cosine u, I have to, oh, what? Alright, so this is my 2 cents on, like, hey, let's say I don't know how to do this derivative. You know what I mean? I don't know how to take cosine 2 theta. And so I'm going to say the derivative of my function of like cosine 2 theta. So we're going to do derivative of cosine 2 theta with respect to theta. Let's say I just don't know how to do this, but I could do the derivative of my function with respect to u, and then du d theta. So this is the chain rule, where it's just like I don't know how to take the derivative of 2 theta, but I do know how to take the derivative of cosine of x, cosine of u, you know, derivative of that with respect to u, with respect to x, is just and then here's the other thing. If we're getting into this, cosine starts up here at 1 and then drops, you know, kind of parabolically a little bit. If you want to get super technical, I would do 3 segments, 1, 2, 3 segments, and then I would go up. If this is 1 segment, I would go up. Let's see. Then I would go up 2 segments. So if you're trying to do sines and cosines really legit, I would do 3 over 2 up. This is going to be 0.5. This is going to be 1. This is going to be 30 degrees, 60, 90, or 0.5 radians, 1 radian, 90. Sine is a very linear. It's almost linear all the way. This is a approximation for sine. And then cosine, cosine is basically like this. And then you can just round it out. When it comes to the derivatives, all we want to know is that, hey, this slope is a slope of 1, but this really shows this slope is 1. If we're in radians, 0.5 radians, 1 radian, you know what I mean, 1.5 radians. And it's basically, this is pi divided by 2, which is 1.57. This is, you know, pretty close to 0.5. You know what I mean, this is pretty close to 0.1. But this is 0.57 divided by 3 segments. Because 3.14, it goes to 1.5, and then 0.07. That's where that 7 comes from that 14. Sweet. So derivative of sine, meaning that if I throw in a value of 0, I should get 1. That's the slope right there. And when I throw in a value of 90, I should get a value of 0. So what function does that? The cosine. Throw in a value of 0, I get 1. Throw in a value of 90, I get 0. The derivative of cosine, however, hey, look at this. It actually slopes down. So we have a negative slope right here. And when I throw in a value of 0, I should get 0. Hey, that's sine function. So sine of 0 is 0. And when I throw in a value of 90, sine of 90, hey, I get a slope of 1. Ooh, sine of 90 is 1. My slope is negative 1. So that's the only thing, you just got to visualize. So how I do this fast is like if I have derivative of cosine, I draw the cosine and say slope is negative and sine is 0, 0, so it's just negative sine. If I have derivative of sine x dx, here's my sine equation. Hey, my slope is 1. Well, cosine is 1. So the derivative of sine goes to cosine. Hell yeah. Alright, hell yeah. So we are ready to turn this into a u substitution, because we can take the derivative of, we can take the derivative of that with respect to u, and then du d theta. And then these cancel, and that's the same thing as taking the derivative of that with respect to theta, which we just don't know how to do. So that's what the definition of, why u substitution is useful. And I'm going to go through this. So u is equal to, let's write this out. So I'm going to have derivative of cosine u divided by, and the derivative of u, and then I'm going to have du d theta. Alright, so my u term is 2 theta, and I need to take the derivative of u with respect to theta and put that right there. So du d theta is going to be 2. Hell yeah. And so that term goes right there. And so now I can take the derivative of cosine u, which is going to be, so the cosine, so it's going to be negative sine. So we have negative sine u times 2. And so now I can throw back my u. So this is going to be negative, the 2 comes in front, sine, my u term is right there, 2 theta. You know what I mean? So, that's a lot of work just to be like, oh yeah, I remember, just like pop out the 2. And then take the cosine just like normal. Or you can just say, hey, I'm going to take the cosine of just a generic angle in here. So the cosine of this is just going to be negative sine theta, but then I got to take the derivative of the inside. You know what I mean? And then I got to take the derivative of the inside with respect to theta is 2. You know what I mean? Because that's similar to what you would do if you had, something like this to a power, and you had to use u sub, this is u squared. You know what I mean? If you just had x squared, good to go. But if you had x plus 1 squared, well, hell yeah, you kind of just do all those terms, like bring down the 2, keep this as a unit, x plus 1. That's basically the u substitution part. Bring down the power, and then take the derivative of the inside. So, you know what I mean? There you go. All right, so the derivative of this term goes away. And the u substitution here is going to be negative sine. And so we're going to have that term. We're going to have a negative. We're going to have a sine 2 theta. U substitution for this. So I'm going to have u is 2 theta. Du is 2. Du d theta is 2. And because the other way to do this that typically gets done is like, hey, I'm trying to take the derivative with respect to theta of sine 2 theta. No, never mind. I'm sure there's other like little half tricks to do this, but I'm just going to stick with what I know. So I don't know how to take the sine of 2 theta with respect to theta, but I do know. So I don't know how to do that, but I do. I can take this with respect to u, sine of u, and then du d theta. See how this just even geometrically works out. These cross out, and this is the same thing as taking the derivative of this function with respect to theta. Cool. So u is 2 theta, du d theta is 2. So this term's going to be 2. The derivative of u is, so if I have sine function, it's going to be cosine. So this is going to be cosine u times 2, bringing the u back in, and u is 2 theta. So we have 2 cosine 2 theta. All right, hell yeah. So this term is just going to be 2. Yeah, so let's grab a fresh sheet of paper. And the other thing that we're going to do is take the derivative of this and set it to 0. So we have the derivative of sigma x1 with respect to theta is equal to 0. This term goes away. This is going to be sigma x minus sigma y divided by 2. And then we're going to be multiplying by 2. And we have a negative and sine 2 theta. This is plus, so it's still a positive. We're going to have a 2 tau xy cosine 2 theta. This is equal to 0, which is the same thing as putting the equal sign right here, doing that. These two cancels. And so, and then what we're trying to solve for is the angle. I have a sine of an angle and a cosine of an angle. And we have an equal sign right here. Let's get the cosine divided by the sine. And this becomes tangent. So now we have tangent of 2 theta is equal to, so this term moved. And now we have 2 tau xy. And now I'm just going to divide by sigma x minus sigma y. And what they're gonna show here is like, hey, let's call this tau xy is sigma x minus sigma y divided by 2. You know, because we've used that term throughout, and this term became visible right there. And so this is the angle, the tangent 2 theta. This angle right here is one of the maximum angles. It's one of 2 angles that gives us sigma. Well, it's one of the 2 angles that gives us sigma Whoa, whoa, whoa. Is that true or not true? This is... Alright, so I think that this just gives you two different angles that satisfy this equation, sigma 1, sigma 2. So one can be max and the other is like, you know, is related to principal stress. One's max, the shear is 0, and the other is a value. So that's what happens. One of these at some point is max, the shear is 0, and the other is just a value. So how they go about solving for the max, because we still, what we need to do is we need to solve for this angle, which we can probably just do right now. You know what I mean? Like that's this equation. You're just like, okay, I could take the inverse tangent of this side and then divide by 2, and that's going to give me the angle, right? There's going to be 2 of them, so we would have to double check which one is the maximum. And so I think that's where they're going to use this diagram. So this is pretty wild. Like I've started to do this with my geometry. And so what we're saying, this diagram, let's spell it out. So we have the tangent of 2 theta. And now we're going to call this theta p because it's a principal angle. But again, there's two principal angles. I mean, if there's a principal angle at 25 in the x direction, the y direction is 25 plus 90, like 115. And one of those values, maybe the y value, sigma y1 is the max. And then so you would say the max angle is at you would rotate the element to that angle. Or do you just say you would the angle is 25 at the max, but sigma y1 is the maximum value? However they say it, who cares? Anyway, but this part is pretty cool. So we have this principal angle, and we know it's a tangent. So we're gonna so the principal angle times 2 is this angle in the tangent. So tangent of an angle is going to be opposite over adjacent. So this is a ratio. So anytime you have a tangent of an angle, that's going to be a ratio. So if you have a number over here, just divide it by 1 if it's a number. But here we actually do have a fraction. And so we're going to put this as our tau xy part divided by, and here's the adjacent. So opposite over adjacent. And then we're going to get the hypotenuse. The hypotenuse is just Pythagorean's theorem. This squared plus this squared. So nothing too scary going on there, and then the square root of it to get that length. Now, what we're going to do is we know that this is a principal axis, and so what we want to do is solve this equation. And we just want to get the max value. So we just want to get sigma, we want to take sigma x1 and get sigma 1. And this will generate the maximum value. Yeah, maybe I have to go to the textbook to see if like this always generates sigma x1 to be the max, where sigma y1 is the max. I kind of forget about that. Anyway, so let's run through this geometry because it's kind of fascinating. Where we have a cosine 2 theta here. So let's go to this diagram, and if this is our angle 2 theta, and if we're throwing theta p is in here because that's going to give us one of the. This is going to give us I still don't know if it's going to give us just one of the principal stresses or the max stress. I kind of forget about that. But hell yeah, so if we have cosine 2 theta, and here's our angle, here's the adjacent, and here's the hypotenuse. Cosine of this angle says adjacent over the hypotenuse. So let's just start our way in. And so we're going to take this divided by that. It's ugly, and we're going to throw that in right there. It's not too bad, though. And then, so for this sine 2 theta, here's our angle. Here's the sun shining rays. This is the sine side. So sine of an angle is the opposite divided by the hypotenuse. So this term, sine 2 theta, is going to get replaced with tau xy divided by this. And then, even right there, you could stop. Because even just right there, what we have just done is got rid of our angle. So now this equation becomes sigma 1 or 2. I don't know. You know what I mean? I'll have to look in the textbook whether this is the max or it's just it's either 1 or 2. You know what I mean? You get like this equation, 1 or 2. But anyway, because once you throw in those values, those ratios, you no longer have an angle. You know what I mean? So you are solving for sigma 1, where here you could easily solve for this angle, you know, using your calculator or whatever methods. But you're going to have to get two angles between 0 and 90. You're going to get two different principal angles. And do the principal angles happen between 0 and 90? Damn it, I kind of forget about that too. But anyway, the whole point is to go through the rigorous math, and so let's do that. Yes, we got to, let's grab another sheet of paper. Alright, so sigma 1, and I don't know if it's 1 or 2. Sorry about that. I should take a pause and actually see, but whatever. So we have sigma x plus sigma y. Like those things are just like I don't mind throwing asterisks on the page, and then within a day or a week, like just getting solid on. You know, so I think it is good to, you know, like throw yourself out there, like do your math online. You know what I mean? Because you're gonna say wrong things, and be okay with doing that. You know, be okay with making hella mistakes, because it's just so fascinating. If you do that, mentally you're going to catch them so much faster because you already put yourself out there. You're just like, oof, yep, no, I heavily improved this week on that topic or something like that. All right, so we got this divided by 2 plus sigma x minus sigma y divided by 2. This cosine 2 theta, that's where they just use this r term. It's just like, I don't know, you know, and they give these equations. I don't like that, whatever. I would just go for it, you know what I mean? So cosine 2 theta is going to be this. So we have sigma x minus sigma y, divided by 2. And then that's going to be divided by the square root sigma x minus sigma y divided by 2 squared. I'm just going to do t for tau squared. And cool. And then we have plus t for tau, and then the sign. That's going to be this. We're going to have t divided by the square root of, and this is where, you know what I mean, we're trying to simplify this anyway. So anywhere where I have a parentheses, it just means that we have one of those. Cool. So even like right here, this part stays the same. So we have one of those plus that squared divided by the parentheses. And that's what we have under the parentheses, plus t squared square root, and this is what we have under the parentheses. So there's no reason to write a mile, and this can really help, you know what I mean? And so, cool, denominators are the same, so we can just add these two and use the same denominator. And then all you have to do is rationalize the denominator, and it pops out. So you're going to multiply top and bottom by the square root of that. And again, t is tau xy. In the parentheses is sigma x plus sigma y divided by 2. And when we do this, cool, we're just going to get, we're just, like the square root goes away and we just get one of them. And I'm going to put that in extra parentheses. On top, we're going to have still one of them, and that's going to cancel the one on the bottom. And then we're just left with that in the parentheses. So after all that, we have sigma 1 is equal to sigma x plus sigma y divided by 2 plus sigma x plus sigma y divided by 2 plus tau xy squared. Alright, hell yeah. So we got some more juice, and let's try to answer our own question. I think we are, because this definitively is sigma x. You know, it's this plus the square root. And so that's what we have here. Sigma 1 is this plus that square root. You know what I mean? So I betcha if we throw in, if we solve for sigma y, if we throw in these into here, hey, this negatives and this negative is probably going to pop out to get the lower term. So yes, so that answered my question. If we do it this method and we solve for sigma x1 and we throw in this relationship, it is going to give us the max value for our sigma x1. But what happens there is that let's say, and is it true that there has to be a maximum between 0 and 90? I kind of forget. It's just the fact that we double the angle. So if the angle is not like a 90, that means that, or if the angle is like a 70, 2 times 70, that's going to give me a value of 140 or whatever. I don't know where I was going with that, but anyway, so let's solve for this one, throwing in this geometric relationship. And again, it's you could have been done like what we did is we solved for this. We said that the tangent of 2 theta gives us this, and so we can just solve for theta, but we're going to get 2 answers, and it's in 360 degrees, I think you get 2 answers. I think that's how it works. Man, I'm so bummed that I don't know like how many like, yeah, you're going to get a maximum every 90. Yeah, right? Like sigma x1 has to be either, you know what I mean? It could be a principal stress at 0. If it's not, there has to be a principal stress you know, between 0 and 90. But this equation though says that, hey, you might not get that. You might get one of the, you might get a, so between 0 and 90, you might get a place where the shear stresses are 0. But that doesn't mean you're going to get a principal stress there, where the other one might be your maximum. So yes, so I think I'm answering that one correctly. That your maximum angle is going to be somewhere between 0 and 180, and so so that makes more sense, because between 0 and 90, for sure you're going to get a principal stress, but there's a chance that this x direction is the smaller normal stress, and then the y direction is your max. But if you throw in this relationship, it will generate the max stress. Yeah, and I guess this just generates the max stress. It doesn't tell you what angle it is at though. So so that's also where we use I think that's where we use these 2 equations, and I might have to look that one up. But because we have a sine component and a cosine component of these principal, yeah, so this is the max angle. So, you know, when we solve for sigma 1, it's going to be the positive value. That angle is going to be associated with sine 2 theta max and then cosine 2 theta max. And because those 2 things are defining that equation, this is only one location on a circle, and so that's going to be the angle that occurs, I guess. Sorry, that sounded awful. All right, but let's do this. So we're going to solve for sigma 2, which is sigma y1, using, inputting these into. So we're going to have parentheses minus, now this one, sorry about that last one. This was a plus. So this was a plus value. These were all the negatives. So when I put a parentheses, all of these jived, but this one was different. This one had to be a plus. So let's still keep this on the easy, and I'm gonna say this first term is gonna be a bracket. Hell yeah. The second term is gonna be that parentheses. It's gonna be the one that pops up. Sigma x minus sigma y divided by 2. And then we're gonna have cosine 2 theta. That's going to be this term again, divided by everything under the bracket, everything under the square root. Then we're going to have minus t times t again, divided by this, square root. And hell yeah. So now just even doing something like that keeps the geometry, or it keeps the algebra pretty simple. Same thing. This is going to be sigma. It's going to be that squared, and this is going to be tau squared, tau xy squared. We can add those two together, and minus a minus. We can keep track of that. So we're going to have minus. We should probably factor out the negative. So we're going to have -1 outside of all this jazz, and we're going to have squared plus t squared divided by just one of these now. So that's all we did. Factored out the negative, and because we have denominators are the same, we can add these two on top and then just use one of these denominators. Now we can rationalize. So I'm just going to multiply top and bottom by that square root term. And what happens is that the square root goes away, and we get one of them. And that's going to cancel out with that one. And we're just left with that. And we're left with the subtracted value of it. So that gives us that initial term subtracted by what's under the square root. And that's under the square root. So yeah, so there you go. So yeah, so that officially makes your sigma y term your your second, not your maximum, but your second, your other principal stress. And how that looks is like, hey, if this is the x1 direction, y1 direction, sigma 1 maxed, and then hey, this one's not as maxed. This is sigma 2. This is still sigma x1. This is still sigma y1, but we denote it with a different. But we just denote it as a max. You could just say this is sigma x1 max, and this is sigma y1 not max but principal. You know what I mean? So yeah. So that's how we. You know what I mean? Like one is max and one is not max, but they both are associated with this principal axes where there's zero shear. So that's the take-home point, zero shear there. All right, hell yeah. I don't know if I'm going to get into this the equation, the angle based, but that we'll probably have to try to finish. That's going to be the roughest part. So the next thing is let's try to find the max shear force. And I guess I get this. You know, we're going to take the derivative. We're going to set it equal to 0. And then we're going to get exactly what we just kind of got before. And then we can get these two terms, sine divided by cosine. And we're going to get something like this. So the tangent of the angle that makes the shear force max is going to be tangent of 2 theta s. And that's going to equal this. And we're going to set up that same ratio over here. I think we do that. where, you need to set up a different triangle, where if this is theta x, so tangent is opposite divided by adjacent. So now my opposite is sigma x minus sigma y divided by 2. And my adjacent is, let's say, just negative tau x y. So, so I'm going to have negative tau x y. And then over here I'm going to have that, I'm just going to put this in parentheses. I'm just going to have that term. So that's what's going to happen there. So let's go through that process. Alright, hell yeah. And this was just, I just wanted to do this as my first rodeo to go through the entire process of finding these. So we're going to take the derivative of this. Let's try to do it a little bit faster. So there's a sine graph. Derivative is going to be cosine. We're going to pop out a 2. So we're going to have negative sigma x minus sigma y. The 2 cancels that 2. I just did that. And then we're going to have and cosine. So cosine 2 theta. Here, if we have the cosine graph, it's going to be negative sine. So we're going to have negative 2, so we're going to pop out that 2, sine 2 theta. This is the derivative. We're going to have to set this equal to 0. And so that's the same thing as, let's say, just doing, getting this to the other side. This would become positive. So there you go. And then I'm going to take this under here. And then, so now I have a tangent of 2 theta is equal to, and I'm going to bring the 2 down here, so we have negative sigma x minus sigma y divided by 2, and then also divided by tau xy. So that's exactly what we get right there, and we just drove it. Hell yeah. And then so we have, you know what I mean? So our new R value, our hypotenuse, is going to be this squared. Oh, that's going to be the same. And then we're going to have, yeah, so wherever you put the negative, it doesn't really matter. And this is going to be the same. Yeah, so we're going to get the same R term. So that's hella sweet. And but we just have to throw in these values into here. So sine 2 theta, let's write this out. So we're going to have negative square root. I mean, just this term we're putting in brackets. We've used that before. Sigma x minus sigma y divided by 2 is that bracket. Sine 2 theta is this divided by the, you know, hypotenuse. So we're going to have tau divided by the square root plus t. Cool. So that's that term. And then we're going to add it to I just mental block. But okay, so now we have, oh yeah, so that it is, it's opposite. Yeah, so yeah, is that going to show up? Or is it going to work out? Anyway, let's find out. Because the way this is written, tangent is the opposite, so that's going to put this value on the opposite, and divided by the adjacent, it's going to put this value on the adjacent. So when I go here to throw in these values for sine, sine is, oh, see, did I already mess it up? No. Sine is, yes, I messed it up. So there we go. Yeah, I knew it wasn't going to work out. So we have, this equation is negative this, and then, and that's that part. The sine of this angle is the opposite divided by the hypotenuse, and here's my new opposites. So here is for the shear, and then here is for the shear. So these are the new values. So I have this divided by that, and then we'll have that squared, right? Cool. And then we're going to subtract, this equation. We're going to add t, and then the cosine is going to be a negative t divided by the hypotenuse, which is that term. Sorry, this is a squared. Okay, so now when we add these two, we're going to have a negative and a negative. We're going to have that same thing. Factor out the negative. We're going to have that squared plus t squared, all under that. We're going to double it. And then up top, these are going to equal this 1. So that's going to cancel, and we're just going to have that. So we're going to have a negative r. And our r term is the exact same. So that's pretty sweet. So, for this, why is that all we get? Yeah, I guess that's all we get. We don't have an extra term out front. I didn't realize that as I was going through. So we just have this value that we simplified into that hypotenuse term. So yeah, so for this max shear, it is just this hypotenuse term. And see how they didn't just write, hey, this max shear is r? That's why I don't like this simplification. Might as well write it in, big and clunky. I don't like the idea of just saving and calling it a letter. But anyway, I guess I'm warming up to it. I think it provides confusion. Warren, it's kind of fun to see if you could do the simplifications. Alright, so that's going to be the max shear. And, for our example problem, all we have to do is just throw in 3 values, sigma x, sigma y, and shear, to get the max shear. And sometimes that's the only thing we're interested in. You know what I mean? So if we don't have to bother too much with the angles of where these things occur, we at least have found, given an angle, we can find the stresses and the normal and shear. And if I just know the normal and shear, I can find the max and then the other principal stress and then the max shear. So the max normal and the other associated principal and then the max shear. I'm going to look at my book just to see how, because yeah, there was this special thing where it's just like if you do have this as cosine and this is sine, these two are one angle. Where if you just have something like tangent of 2 theta, hey, there's going to be a couple angles that match. But if you have this correlation, so this spells it out. So if I was trying to find, and I need to see where they drove those two, because you only need one actually. That's what it shows right here. If you throw in this value of r, and then take the inverse sine of that, and then divide by 2, that is going to give you that principal angle. That's what that number 1 means. And so, and you could do it with either equations. And so I need to see where those come from. And then we'll finish with angles, just so I'm satisfied. But we did it all the way up to these equations, so we're doing pretty good. The other thing that comes out, just out of the wash, is just like, hey, let's say we found sigma x1 and sigma y1. Let's say we just added them together. We rotated the element, and now we have a new sigma x1 and new sigma y1. If we added those together, they're the same. They're going to be the same number, same value as adding the original unrotated sigma x, sigma y. You know what I mean? So it's just, that could be a check on reality, and it's just a property that pops out of this. So, and again, there's a lot of properties that pop out due to the geometry that are, probably even extra to the main things that we're looking at and wanting to find. All right, so let me look through the angles, and hell yeah. All right, hell yeah. So I think we're on the home stretch, and I looked up what these angles are. But there was one catch on this. So when we do the shear stress and we rotate it by 90, so if we throw in, so let's say we want to find, we were saying our original thing looks like this, positive face, so shear is that's going to be positive shear, and it's going to be associated up here. And so let's say I just wanted to rotate this element 90 degrees. You know what I mean? So now my so my x1's up here, my y1 is over here, and this is going to find me the shear on this face. And when we do that, when we throw in theta is 90, this is going to be, since the angles are twice, this is going to be 90 times 2, so we have cosine of 180, and that's going to be a value of a negative. So it's going to be a negative 1. Sine, so if we have 90 times 2, hey, the sine component 0 has no vertical component, so this term goes away, and this becomes negative. So we have negative tau xy. And so that would say that this shear is going to be on this face, this 90-degree face, in the negative direction. But check it out. That is synonymous with positive shear. Positive shear says, hey, this is positive, this is positive. If we start out with this x and y face, positive x face in the positive y direction. And once we know one, we know them all based on forces in the y and moments. And if we rotated it, well, we would just have this, you know, this going on. Oh, no, pen's running out. And if we rotated it all the way 90, well, it would just, if I rotated this 90, I would have, oh, man, am I bumming out now? Oh. No, yeah, like, I don't know what I'm thinking. As this rotates, these for sure change. These shear forces change, and as we rotate to 90, we get right back to that. So when I rotate this 90, this one on top is that direction. You don't just get to rotate it to where that arrow is now facing that direction. Because if I rotate this 90, it still has the same... And that actually goes back to what the beginning part of the chapter says. It's like, hey, this is a point that has stresses going on, you know, normal stresses and then shear stresses. And just because we rotate it, those values are going to change, but that is still synonymous with the equilibrium of this point. That means, you know what I mean? And so you can't just say that we have positive shear, and then if I rotated this element 90, that this arrow would somehow go that way. We definitely can't have that. So that's where, if I do rotate this to a 90, it's going to look the same. And but my new axes is x1, y1, and my shear is going to be on a positive face in a negative direction. So that's where that negative would pop in. So that's very good to go over that. All right, let's see if we can go over some of these angles. And the first thing was to look at this tangent equation. And so yes, this tangent equation is well, a couple things. There's going to be two angles that satisfy this between 0 and 360. So a full circle, you're going to get two angles that satisfy. Because it's a double angle, you know, because I'm solving for the angle and multiplying by 2, that's how we get two solutions in 360 degrees. That means that we get two angles to form in 180 degrees. One is going to be associated with the max, sigma 1, and the other is going to be perpendicular associated with sigma 2, or vice versa. So we can say, so I was right that if we start at 0, and those aren't the max normal stresses, we start to rotate. Between 0 and 90, we are going to get a principal stress. We just don't know if this is going to be the max or just the other value that's principal. And so, so between 0 and 90, we're going to get one of those solutions. Because this is multiplied by 2, that means that the other... and because this is multiplied by 2, that means one of the solutions is going to be, or how do you say that? Is going to be 0 to 180. I mean, because if one of the solutions happens between 0 and 90, the other angle is just perpendicular to that. It's just that angle plus 90. But if we're solving for this 2 theta component, if we're solving for tangent of this, this angle is going to double, and then you're going to have to add 180 to get to the other solution. So the solution to this 2 theta p will be 180 to each other. Where if I'm just solving for the principal angle and one of them, one's going to happen in 90 and the other is going to be perpendicular to that. And that would make sense from the fact that the principal angles, when we have an element and it reaches its principal angle where there's no shear stress, you're going to have a perpendicular. One's going to be big, one's going to be normal. This one's going to be big, this one's going to be normal. And so that's going to be associated with, if this one's the larger one, taking an angle from the horizontal, that's going to be theta p. So that is going to be theta p. But we just have to keep in mind that because of this 2 here, we're going to have 2 solutions between 0 and 360. So what they say is to run through this whole ordeal, you know what I mean? Like, use this, that's the thing. It's like, hey, if you're just trying to find the principal stresses, you don't do the derivation now. Like, we already did it. Like, we went through, you could throw these in your calculator and then, do a max-min type thing, but we just went through the derivations, and to get this, to get both of these terms. So all you'd have to do is take a problem and throw in sigma x, sigma y, and tau xy to get both of these, because we have a plus and minus. Once you get both of them, then what they say is to find, and this is going to give you 2 angles. You know what I mean? So if you actually solve for theta p, you're going to get 2 solutions. And I guess in more general, if you solve for 2 theta p, you're going to get 2 solutions to that 2 theta p, however you want to think about it. But anyway, so you're going to get 2 angles. So just theta. Theta p is going to be 2 angles. You can throw them back into, you can throw each of those angles. So you have 2 angles. Let's throw one of those angles into this equation and get a value. Throw the other one into this one and get a value, and then see which angle was associated with the max. And if I already solved for the max, then I could just throw one value into one of these. I don't know, however you do it. But then you can see what angle actually generated the max for sigma x1. Because that's kind of what we're interested in. We're interested in this equation, sigma x1, finding the angle where sigma x1 is maxed. And so even for this, determine the max shear stress and then determine the principal stresses. Oh, that's interesting. So yeah, so here they show the angle from x to the principal angle, but they just show the principal angle too. But the principal angle to the maximum is going to be this plus 90. You know what I mean? So that is going to be associated with sigma 1. Oh, and I'm glad I went over this, because it's just like, well, can't you get these by rotating 90 degrees? It's just like, why would you have to rotate more than 90 to get the max principal stress? Well, it's the fact that you could rotate in the negative direction. So keep that in mind too. But in this, you know what I mean? If we rotate 75.2, it's going to be a principal axis, but this is not going to be your max normal stress. The theta P1 is going to be the angle associated with, and that would be rotating, and you can still think of this as your x1 axis, and this, but if you did that, if you said this was your x1 axis, this would be your y1 axis, because we're rotating that axis all the way around to here. And so so the way it's done right here is they're saying that this is the x1 axis, this is the y1 axis, and it just happens that this x1 is not the max. So this angle is not associated with the max angle. It's associated with a principal angle, but not the max. Other way to look at it is you could just rotate down a small, negative 15 degrees. And if we did that, this would be x1, and this would be y1. And so, yeah, it's kind of fascinating, just kind of the different ways to look at these, because, yeah, when it gets down to the grit, yeah, those things are going to pop up and be head scratchers. All right, so this is going to generate two angles, where when we got this relationship and we got these two equations for sine and cosine based on this triangle, the first triangle. What they say is that this is going to be your principal stress. The principal stress is going to be the angle that satisfies both of these equations. And unless I look that one up again, I have I don't even know how you go about that. I apologize. But we do know that the max shear stress happens at 45 degrees towards the principal stress. So whatever principal stress we find, it doesn't matter if it's P1 or P2, the max stress is just 45 degrees to that. And we have shown that if we find one of those and we go 90, that stress becomes negative, but still it doesn't change the actual, let's see. You know what I mean? I guess you just have to keep, if you do rotate things, keep track of where your x1 and y1 is. And if you're finding the shear, you're finding the shear on the x face. And if it says it's negative, that would just mean it's positive x1 face in the negative y1 direction. But that can, you know what I mean? So just keep that in mind, that sign convention is something that you're going to have to look at and be aware of. So if from those transformation equations you get a negative shear, tau x1, y1, that just means that you have to locate the positive x1 face and then go in the negative direction of y1, and then write that onto your square, and then find the others. So all right, so we have these two relationships for tangent, for the principal stress, the max principal stress, and the max shear stress. And these two are very similar to each other. This one's a negative. If we got rid of the negative, all it is just the inverse of these. So I can say that tangent 2 theta p is equal to the negative 1 divided by tangent 2 theta s. And then so what we have here is we have sine of 2 theta p divided by... Alright, we're back. So we're taking tangent and then having this as sine divided by cosine. So we have cosine 2 theta p. This is tangent, but it's downstairs. So we have sine 2 theta s, and then we have a negative cosine 2 theta s. We want to get these set to equal to 0. And so I'm just going to get this one to the other side, add it to the other side by doing this, adding equal to 0. Booyah. And so now we have the denominators. We want to make sure the denominators are the same, and then add these two terms. So we need to have a term down here that's a sine 2 theta s, and so we have a sine 2 theta s on top. And then over here I need a cosine 2 theta p and a cosine 2 theta p. So let me write this out. So we have sine 2 theta s, sorry, there's no 2 there, sine 2 theta s, sine 2 theta p, plus cosine 2 theta s, cosine 2 theta p. This is all going to be divided by a common denominator. Sine 2 theta s, cosine 2 theta p. This is equal to 0. Now, I did not know, like, you know what I mean, that you could do this. This was a new one to me. If I have a plus b divided by c is equal to 0, you know, this is the same thing as saying, like, if I have x and then x plus 1 is equal to 0. To solve this, you would say that I have two equations here. This is satisfied if this is 0 or this is 0. So x is equal to 0 or x plus 1 is equal to 0. Two equations. And so that's what we have also in something like this, is if the numerator is 0, then it satisfies this. So this can just become a plus b is equal to 0, and if I solve for this, I'm good to go. So that's what they do. They take this numerator and just solve for it to 0. So we're probably going to get, and I should actually look to see what the next steps are. Like what would they do? Well, let's just try it out. So we're gonna get a negative sign. Sine 2 theta s, sine 2 theta p is equal to negative cosine 2 theta s, cosine 2 theta p. Yeah, I need to see what they do. I don't think I can do this one. Alright, hell yeah, I am glad I wasted no time, because what we're going to have here is we're going to have, and I guess I didn't even need to get it to one side or the other. So we're going to have cosine plus sine, or vice versa. And if we have a sine, and if we have a plus here, we're going to have a minus here. So these two terms added are going to be cosine of sigma s, theta s, sorry, which is the angle of max shear, minus sigma p, which is the principal axes. And that's what this is going to boil down to, and that's going to be equal to 0. Cosine of what is equal to 0? Cosine of what angle? If cosine of 90, cosine of 90 degrees makes this equal to 0. And is that where they, and my bad, we forgot the 2 here, because cosine of 90 degrees, and then also cosine of 180. Let's see, cosine of 90 is 0, and cosine of negative 90 is 0. So yeah, if they're doing the full circle. Yeah, that's the crappiest part about trigonometry, is like wanting to, you know, do everything in every quadrant. I don't know. Sometimes I just have to throw in the towel in trigonometry, but whatever. But this one's testing me, because yeah, you have to, because this double angle, we have to evaluate something between 0 and 360. Definitely not just between 0 and 90. And I guess even if we didn't have a double angle here, if I did something between 0 to 90, that's going to affect something perpendicular between 90 and 180. So I guess I get that. You know what I mean? So that's kind of what's happening. Yes, sure, something happens between 0 and 90, but it's also associated with a perpendicular surface from 90 to 180. And because of this 2 times the angle, all that's going to be doubled up, and so we have to focus on the full three. So 2 things are going to happen in 360. But with this, you're going to have cosine of 0 is 0 at 90. So cosine, all sine, all vertical, and then negative 90. So positive 90, negative 90. So hell yeah. So we're going to have 2 theta s minus 2 theta p is going to be positive and minus 90. And then divide by 2. So we have sigma s minus sigma p is equal to positive negative 45 degrees. And so what this says is that the difference between the shear and hopefully I even wrote this right. But yeah, let me flip to the page in the book, even just so you can kind of see. Might as well. This is chapter 7 stuff. But hell yeah, this is just before Moore's circle, which has got to be the hardest thing. I never learned anything. It'll be all new to me, but that's my goal, is to get there. Get to the Moore's circle. Alright, so this next page should have it. Ooh, no. Whoa, what the hell, man? Sorry about this. A couple pages back. So there it is. So we have sigma s. Oh yeah, so sigma s is the principal plus or minus 45. So that's how they simplified that. They just said, hey, let's solve for the angle of max shear is going to be, hey, it's going to be, get this to the other side, it's going to be the principal stress plus or minus 45 degrees. So if I know the principal stress, whether it's principal 2 or principal 1, I can find the max shear just by going plus or minus 45. And it really doesn't, I was going to say it doesn't matter what direction the shear is. I mean, the shear is at its max is going to be I don't know, it's going to be associated with the particular direction. I put it that way. If you can know that direction, then hell yeah, you know all the other directions. Arrows are going to go away and towards each other. But I guess, what was I thinking on that? Alright, hell yeah, I don't know if you can see this, but this red line is going to graph out shear from negative 90 to 90. And so, and what we're going to have is, if this is the max principal stress, we move 45 degrees and we get a max shear. Move another 45, we get a max principal stress. So that just kind of shows you that those are 45 degrees apart. And hell yeah, the shear stress is going to be negative at some sort of angle and positive at another angle. But we showed that and how to keep track of that. If you have a particular angle, you know what I mean? If I move this up to the x1 and this to the y1, you know what I mean? This is going to be a positive shear. Cool. But if I move this x1 kind of farther, if I move it all the way to the y1, probably what's going to happen, because, I mean, it's just by if I'm saying this originally at theta is equal to 0, has a shear diagram that looks like this. And I rotate this up to, we already said that, if I rotate it up to here, and so let's just do that. Let's rotate x1 up to here. That means y1 is this way. And it looks like I'm going to have a shear that way, right? And that's going to be a positive face in the negative direction. So, that's where you're going to have negative shears pop up. But that negative shear is still associated with the original stress diagram in the direction that kind of makes sense. So, I don't know if I'll probably have to play around with that one more to say it any better than that. But hell yeah, so we did it. We had the sigma s. And so same thing is going to happen here. If you solve for this shear stress, you're going to solve for two different angles if you just solve this equation. We just did the derivation. I don't even know what the hell we did. We just saw that, hey, these two are related by an inverse. And then so we just went through that whole process to show that the max shear stress is located at 45 degrees to the principal stress. So the whole order of operations on this thing is if, like, hey, if you have one sort of angle you want to find, cool. You know what I mean? Throw the angle in and find all three of these terms, move on with life. If the problem says find the maximum, well, know that we already drove these, And so we're going to throw the values into here and find the maximums. And then we need to find the maximum principal stress. The only thing that I didn't cover was the fact that the max principal stress, sigma P1, is going to satisfy those two. I don't think I can figure out that tonight. I think there's an example in there maybe, but for whatever reason I'm not seeing. Trigonometry kind of is hard for me to see that you have like two different solutions, four different solutions around a circle. For this 2 theta, you're going to get two solutions in 360. And but anyway, so when those two are satisfied, then you got the right angle. Or find the max and then use this equation to find both angles between 0 and 360, and then throw those into these equations and see which one is max when which one creates a min and creates a less than max. And then once you find one of the principal, like even right here, you're going to find both principal stresses. So then you can find the max stress just by taking this plus 45 degrees, plus or minus. And then just know that that max shear stress is going to, so if, I don't know, if here's the max shear stress, the angle to it, at 90, every 90 there's going to be a max shear stress. And then every 45 there's going to be a max, or the principal stresses. So that's kind of what happens. So yeah, so if you found one angle for max shear stress, you have found them all. You have found 4 angles for max shear. Cool. Alright, hell yeah. So I think I'm done with this. So that's about it. So thanks for joining me, and that's a video.